Hi again. And here we go. We had a request to do some multiple choice questions from the Winter 20 examination, test 1. Winter 20. Winter 20. And this looks very intimidating, this question. I've got some methods to help you out and to make it less intimidating. Let's quickly go back to the exam, and we're going to need the table in our presence, and I have it here. I think just bringing it over might help. And scrolling here. My picture's in the way. There we go. I don't know, snipping it over. Just bring it over. Trying. Here we go. See if we can make it smaller. Smaller and still usable. Yeah. Shrink this down a little bit. Maybe not. There we go. Getting dots everywhere now. Yeah. Good. Okay. Beautiful. Process of elimination is good here. What peaks show up at about 3? That looks to be about 3.8. And then what peaks show up around, looks like 4.5 if 5 is here. I think I know the 4.5 ones. All of these molecules have something near 4.5. And they're all esters. So I'm going to start with the 4.5 triplet. What does triplet mean? Triplet means only one thing. 2 neighbors. 2 plus 1 equals 3 is called a triplet. This H here works because there's 2 neighbors. This H here works because there's 2 neighbors. 2, 2, 1 neighbor. Hey, got rid of 1. And this H here works because it has 2 neighbors. Okay, every time you can get rid of 1, you're getting towards your answer. I'm also going to go to the 3.8 because it appears in this molecule when there's only C's and O's and Cl's that the Cl puts something around 3.7. That looks to be about 3.7 with 5 neighbors. Oh, I think this is going to help a great deal. How do I know 5 neighbors? No, well, 2 neighbors causes a triplet. 5 neighbors causes a sextet. Let's put that in a different color, shall we? 5 neighbors on the C that has the H with the Cl. So we're crossing off molecule 1, or A. It's not that there's 2 of those, it's there's only 2 neighbors. I don't like my red X here. I'm sorry, you got to bear with me here. And put our X's in a different color. Well, that's a green X. We ruled it out for the green reasons. All right, go to the C with this next one. B is a perfect candidate. We're just going to get a check mark. This H has 5 neighbors, as it needs to. This H here has 3 neighbors. It's not going to work out. Don't have to worry about E anymore. This H here has 2 neighbors. It's not going to work out. Oh, plus, we could have ruled this one out from the beginning. Not only is the H part of an ester, but it would go higher than the ester range because it's also a C with a Cl. We could have ruled it out from the beginning, and now we can rule it out redundantly because it only has two neighbors. And I think we're done. The H with the Cl here has only two neighbors. It's a triplet. We're done. Bye. Move on. Yep. This is the only H on a carbon with a chlorine. And we know it has to be the one that's this one here because it's the only thing that works with this molecule's formula and our data over here. You want to waste time and verify everything else? Go ahead. I mean, we got this thing's a triplet at 0.9. It's right there. This thing is a doublet at maybe closer to 1 because it's got one neighbor. It's right there. I mean, yeah. And this thing has three neighbors here, two neighbors there, three neighbors there. It's another sextet. It's right here. Why is the sextet bigger than the sextet? Well, this one has only one H in it. This one has two. Everything fits here, but we're wasting our time. Moving on. I got to go to my next page. On your exam, you'll have only one of these two, but you'll have a molecule. You won't have two of them though, because we don't have 6 hours. We have 2 hours, so your test will be vastly smaller. The problem set is well on its way and will be in tonight. The test guide I'm going to try to work on tomorrow before I leave for Georgia. And it will go question by question, what questions to expect and what questions from Moodle you can look at as the exact same type. We're going to use process of deduction once again here. And I'm looking at the benzenes, and I can't use the fact that the patterns on benzene will be different. Yes, I can to get rid of all of the first three. I just looked a little more closely. Why are these all bad answers? That was pretty easy. Very easy answer.
Okay.
Yes.
Do we go like by the H's in the benzene, like doublet, and singlet? So we have to.
Every H in all three of these has to be singlets. So the answer to your question is yes, and that's why there's a big X through all three of them. All three of these benzenes have the same substitution. It goes hydrogen, then group, then hydrogen, then group, then hydrogen. Every one of these green H's here, and I'm not going to draw them, but they'd be the same here and here. They have no neighbors. No neighbors gives a singlet. This is a doublet. This is a doublet. This is a singlet. This would be a singlet. This would be a doublet. This would be a doublet. This is a singlet. This would be a doublet. This would be a doublet. These all are good candidates on the benzene side of things. So half the choices are gone. And now I'm over here. It doesn't look like I'll be able to use the vinyls. They all have the same vinyl. So don't even look over there. I might use the fact that this one has alpha H's here and here, and I don't see that over here. Where do alpha H's show up? They are down here. So if I see two sets of alpha H's, I might be very happy all of a sudden. 2.3-ish. There's 2.3. Ooh, yeah. This would be a singlet, though. This would be a singlet. There's a singlet at 2. That's a little above 2, maybe. So maybe that is this one for that. And this would be a singlet as well. I'm not happy anymore. I lost my happiness. It's fine. I also noticed the fact that benzylic also shows up in the same region, doesn't it? Look, these overlap a lot. Oh, I can't write on that. I'm sorry. Benzylic at 2.3 and alpha 2.3. So I'm always looking for quick shortcuts. I didn't find it. How about a singlet around 4.5. How do I see that? What functional group do we see here? We see an ether. Where are ethers over here? 3.7. That's above 4. There's 3.7-ish. Yeah. Either one of those a singlet? No. But then you don't get that excited because this H is not just an ether H. Oh, I can highlight it. It's not a problem. It's a 2-category item, isn't it? It's part of an ether, so it fits this category. It also fits the benzylic category here. So it might be this singlet up here. It could be. Because you're normally thinking about a normal CH2, normal 1.3. I'm looking from here to 1.3. You're going over to benzylic, and that's at 2.5. That's this one here. And you're also thinking part of an ether. And part of an ether is over here, 3.7. So 1.3 plus 2.4. And 1.3 plus 1.2. And so we're going 1.3 plus 3.6. I added these two combined effects. And I'm looking at 5.2. 5.2. But then I'm also looking at 5.2 for an alkene. Yeah, 5.2. But a terminal alkene's at 5.0. That's a little under 5, isn't it? So this could be this, but then you wouldn't have an alkene, would you? These have to be somewhere. Every one of our molecules has the terminal alkene H's, which would be singlets. Why? Why do we have singlets? No neighbors. So I think our ether game is over for this guy. Yeah, this would be around 5.2. It would be a singlet, but then you wouldn't have another singlet. I mean, I don't see another singlet for the alkene. So that was a long way to rule this one out. I probably could have ruled that one out easier ways. So we're down to 2. This one and this one. This would be a singlet. It's a combined, again, singlet combined benzylic and alpha. So it would be over 3. And I don't see a singlet over 3. I'm not thinking about that one. How about if we can make everything fit here? We're just going to count it. We already pointed there. This would be a singlet as well. And where's it going to point? It's in this category right here, allylic. Do I have a singlet anywhere from 1.6 to 2.6? Well, there's 2.1 singlet. It's big because there's 3 H's. Fits. Do we have alpha quartet? Alpha 2.4 quartet? We do indeed. Do we have 0.8 triplet? Most certainly do. Do we have another 0.8 triplet? Doesn't really matter which. O inductive effect probably shifted it a bit. Do we have an ether quartet? Ether quartet at 3.7. We do 3.7 quartet. Do we have another ether triplet near 3.7? Oh, everything's just fitting here. I'm going to stop. There's just too much that fits. D is looking like a winner all the way. Right there. And there you go. Yeah, those are not trivial problems. They may have looked trivial the way I went at them, but I've been doing these a long time, and I understand Those are tough. That's why I'm going to cut them in half. This one, everybody has to get points on. You just have to review chapter 5. 5. Index of hydrogen deficiency says, if you're going to get rid of the halogens, you got to add 1 for each. 3 for the fluorines, because there's 3 of them. You're going to lose 3 for the nitrogens. You're going to do 0 for the oxygen. Just don't do anything. So we're adding 1. We went up 3 and down 3 cancels, and then we add 1. So 18H20, what's the alkane with no rings with 18 carbons is 38. How did I do that? 2 times 18 is 36 plus 2. And 38. 18 is the difference. IHD's pairs of hydrogen. And we're going back to choice D. And saving. And then we have some lovely acetal stuff. You know, it's the most important thing on the test. So the one above is going to make an acetal, and the one below is going to break down. Oh no, it's retro. It's where did this acetal come from? All right. Not as hard as it seems. We have to identify this carbon. Where is it in every potential product? It is the only carbon with 2 bonds to O in the whole question. If it has 2 bonds to O in the carbonyl, it means it has 2 bonds to O in the acetal. Or if it was a hemiacetal question, it has 2 bonds to O there. It's good. All right. So, see, they have the same skeleton every time. This is only about stereocenters, this problem, isn't it? Mm-hmm. Okay. All right. The carbonyl carbon can be attacked from the front or the back. Okay. From the front or the back. So 50% R, 50% S. So we're doing, I think we're leaning towards a 50-50, but maybe not. Let's talk about the stereocenter where the carbon with the O has an ethyl. New highlighter color. Carbon stereocenter has ethyl methyl. Carbon stereocenter has ethyl methyl. Ethyl methyl. Now that stereocenter doesn't change during this reaction, so we can cross off. Oh, they're all R. It's a nothing burger. This one, don't do anything up there because it's the same in every answer. So we don't even have to worry about R, S there. But how about the stereocenter that's 1 away from the carbonyl, and it's part of the ring size 6. So 1 away from the carbonyl, part of the ring size 6, and we'll make ring size what? 1, 2, 3, 4, 5. 1 away from the carbonyl in the 6 and makes the 5. So we're talking about this carbon here. This carbon is this carbon here, here, and it's another nothing burger. There's no stereocenters listed down there. Am I starting to unlike my own question? I don't even know. Can we just draw the product and see what's going on? We got that. The thing is going to have 2 bonds to O. Where did those O's come from? This O goes away to the Dean-Stark trap. This O goes away to the Dean-Stark trap. That's the carbonyl O. These O's form the bond. So we're going to have a wedge, a CH2, a CH2, and that O. And what else are we going to have? We're going to have this H here on a wedge and a dash here. that goes to a C with the O here and a methyl ethyl here. All right. Does that look like, is there a mistake in this question? I don't know. Anybody tried this problem? It's just seeing this ethyl. Where did it come from? Where did it come from? I'm curious because to me, it seems like there needs to be an ethyl right here to make these products. No, that would be here. Yeah. I'm going to skip this question. I'm starting to just not like it. Okay. It's good. I won't put it on the test. How do you like that? I do like this question here a lot. This one showed up on every exam forever. You can look backwards. There's never an exam without this question. And this one is just figuring out what the skeleton was that makes this. So we're going to go back, do that thing we were doing before with a highlighter. Got our highlighter. There's the carbonyl carbon. How do I know that was the carbonyl carbon? How many bonds to O does it have? It has 2. All right. Now we need an O attached to a carbon with an ethyl. O attached to a carbon with an ethyl, O attached to a carbon with ethyl, O attached to a carbon with an ethyl. But this O is attached to a carbon with an ethyl and a methyl. Does the same carbon have a methyl? Because if it does here, it means it did here. We don't like that one. This one doesn't even have the ethyl on this side. And it has a methyl on this side. So not liking that one either. Same logic for this one here. We're down to 3. The O with a carbon that has the ethyl. And what size ring is that going to make? 1, 2, 3, 4, 5. Oh, I got to be careful. 1, 2, 3, 4, 5, 6. The O with the carbon and the ethyl, O with a carbon and the ethyl is adjacent to a carbon with a methyl, ring size 5. Remember, O ends up in the ring. 1, 2, 3, 4, and the other end is 5. So we're talking about 1, 2, 3, 4, 5. Does 2 have an ethyl? Check. Does 3 have a methyl? Check. Let's go the other way. Let's go 1, 2, 3, 4, 5, 6. Does on the other side, does the O go to a carbon with an ethyl? O goes to a carbon with an ethyl. 1, 2, 3, 4, 5, 6 ring size. Yes, it has an ethyl. Does it skip a carbon, then go to a carbon with a methyl? Skip a carbon, go to a carbon with a methyl? Yes. Does that go to a CH2, then the carbonyl? CH2 carbonyl. I think we found our guy. Let's see why this is not the guy. This is not the guy. There's the ring size 6. 1, 2, 3, 4, 5, 6. The O carbon ethyl. Oh, this is why I was a bad guy over here. There's no sec-butyl attached to the carbon with the O in any part of this molecule. So I didn't like that. And we already got rid of the other ones. We didn't get rid of this one. The O in ring size 5, 1, 2, 3, 4, 5, has the methyl on an adjacent carbon to the ethyl, and methyl ethyl adjacent. So that part's good. This part was not good because this thing doesn't have an ethyl here. It has it here. That's bad. So A won the day. And moving on. Oh, this is a beast. Better save and take a breath. Okay. I will not have one this large on your test, but it's a good scheme. It's a good review scheme, I'll tell you that. So let's pretend we don't have answers and just fill in what we're supposed to get. This is like a roadmap part 2 with nomenclature integrated in between. 3-phenyl 1-butanol. Phenyl. 3, 4, 2, 1. 1, 2, 3, 4. Got that. So 1, 2, 3, 4 here. Thionyl chloride makes this into a Cl. Magnesium makes a Grignard. Grignard's attacking 3. Benzaldehyde. We better know what benzaldehyde is. That appears on virtually every test as well. And that's going to make, you're going to have a Grignard here, C-. Forget about OH, it's long gone. New bond here to here, O- becomes OH in step 4. Copy all the green carbons. New bond from here to the blue carbon, which has an OH now. Pick the name that corresponds to that, and that's product 1. Whoa, I don't even know how to do that. Okay, that's product 1. Product 1, oxidation. How do you know this is oxidation? The step 1 up there is chromic acid in disguise. And then you're going to do alpha bromination. Stuff seems to appear over and over again. It's going to be X when we're done. So step 1, I'll draw what you get in step 1. Oops, no R, phenyl. Phenyl, CC, CCC. Step 1, ketone. Step 2, alpha halogenation. When it's bromine and acetic acid, you get 1 halogen. You can't do alpha halogenation on the phenyl because there's no hydrogen there. You'd have an octet violation. You put a bromine there. There's product X. I bet product X gets used some other time, but maybe not. Okay, it doesn't. It's just a final product. Product 1 is going to go also. There's another chromic acid in disguise right here. These are the 2 methods of making chromic acid here. Good review item to circle them both. And say they both make H2CrO4AQ. That's chromic acid. So you're going to oxidize to the same ketone we have here, except this time we're going to use a primary amine. Methylamine is exactly what it says. And there's a Dean Stark trap there to remind you. Methylamine is CH3NH2. Exactly what it says. And what happens to a ketone? You're going to make this ketone without the bromine. And ketones with primary amines make imines. Phenyl. Phenyl. Double bond to nitrogen with a methyl on it. So that would be the choice there. But then there's step 3. This is steps 1 and 2 only. Step 3, H2PT. Hydrogen platinum makes product Y. So product Y. My X looks inauspicious here. Step 3, H2PT reduces the pi. And we got a single bond to the N with an H. And as a methyl, you keeping track, you also get a new H there. That's product Y. And acetone and a Dean Stark trap. There's a lot of stuff happening over and over again. Secondary amine right here, secondary Amine reacts with aldehydes or ketones to make enamines. Enamines. Make sure these don't look like they're hitting each other. All right, copy the green. Phenyl, CH2C methyl, CH2, C. Wow, pen's off. Phenyl. We had a bond to nitrogen off of here as well. And we get the phenyl, we get the H, we get the nitrogen. We have the methyl on the nitrogen. Single bond to the acetone. Acetone. Now it looks like this. And it needs to be an enamine. Remember, the carbonyl used to be here. That ends up as part of the ene. Next carbon over, doesn't matter which direction because it's symmetrical, is the ene. And there you go. That is product Z. And that's the top of this page, top of this scheme. How are we doing here? Pretty good. Product 1 going to product 2. Here's 1. Let's do the 1, 2, 3, 4. 1 and 2. We'll get you here. Phenyl, CC, phenyl. And we've made an organolithium. First step puts a halogen where you used to have the OH. Oh, no, sorry, a bromine. Yeah, halogen, but a bromine to be more specific. And then we do our lithium and hexane. The bromine is now an organolithium. Styrene oxide. Oh, tip. Tip. Styrene equals vinyl benzene. There's benzene. It's got a vinyl on it. Okay. Styrene oxide. Ah, oxides are, you take the alkene and replace it with an epoxide. There you go. That's a phenyl. There's styrene oxide. This organolithium is going to attack which carbon? The least hindered carbon. Get an O- on the adjacent carbon. And aqueous ammonium chloride. Interesting choice. That's all I'm saying. Let's do step 3. There's probably a pKa problem in there. That's why I did that. Step 3. New bond here to the less substituted carbon there. Goes to a carbon with an O- and a phenyl. Ooh, CH2 phenyl. Well, not paint. Don't use the paint can. With the CH2 got attacked. CH2 phenyl. And aqueous ammonium chloride is just another acid. Ammonium. We're supposed to remember has a pKa of 10. And product 2. Whoa, we're going to finish barely. Product 2. We have the conjugate base of an alcohol is going to become an alcohol. CH2COH. pKa equals 17. And pKeq, 10 minus 17 equals -7. KEQ, I could ask any of these questions. That's why I'm putting them here. I don't care which one I asked. I could ask any of them. I could ask for PKEQ. I could ask for KEQ. And that's product 2. It's going to hit, we're going to hit product 2 with sulfuric acid and heat. Sulfuric acid and heat is going to do dehydration of our alcohol. So we'll just do that. You're saying, which way do we dehydrate? Do we go to the right? Reminder, there's a carbon here. And that is the answer. We make a double bond there. And that means we got a C, double bond C to a phenyl, C double C to phenyl. There's this CH2. Comes down to a C with a phenyl. Once, twice, 3 times methyl Ph. Why did I pick the double bond in this direction instead of to the left? Answer quite simply, that double bond can resonate with a phenyl. This double bond can't resonate with either phenyl. Easier to make double bonds that resonate. Step 2 is a chapter 6 reaction. It's right at the top of the screen. You're going to make a vicinal diol. Vicinal diol. Let's draw it. You're going to review osmium 8 oxide and tert-butyl hydrogen peroxide in chapter 6, right near the end. It's almost at the end of chapter 6. And vicinal diols are easily made from alkenes doing that method. And you know what we like to do with vicinal diols? We've got an OH here and here. On this carbon, there's an OH. And this carbon, there's an OH. We love making acetals. And how do we know we're making an acetal? We've got our favorite acetone, carbonyl, which is a ketone, and a Dean-Stark trap is a hint for the condensation. So this will be product, what, 3? When we're done. And yeah, we're almost done. Phenyl, CC, CH2, CH2, C, phenyl, C, C, let's see, I'm up to here, and I'm gonna go C, CH2C, there's gonna be O's here and here, and a phenyl off here. Those O's are used to make acetals with what? You need 2 alcohols to make an acetal. What else do you need? An aldehyde or a ketone. Got it. Both of them, during the mechanism, attack the carbonyl. And acetone has 3 carbons. And where'd the O go from acetone? It went to the Dean-Stark trap. So you probably have to circle this picture. And I think we got a lot of good review in. And on Monday, there's going to be even more review. And I hope this was useful to you. And I will see you Monday. Here we go.